All right, so we are at 11. So it's time for hosting our next seminar speaker, who is a distinguished metallurgist from the University of Texas at Austin, Professor Eric Taleff. Incidentally, Eric is one of the persons who actually, I read a lot of his papers when I was a graduate student and got inspired to work on steel microstructures. So most of my work actually has been revolving around his work done in the 90s and early 2000s. So Professor Taleff is actually a Charlotte Meyer Cratton Centennial Fellow in Engineering in the Department of Mechanical Engineering. I'm also a member of Texas Materials Institute at UT Austin, and he's also a fellow, well known in the circles, ASM, TMS, you name it, he's there. He's a Brimacom medalist, and then he is also AIME champion, Matheson Medal awardee, and General Motors Most Valuable Colleague Award. He also won that. So his research primarily focused, as I said, he's a metallurgist. So physical and mechanical metallurgy are his areas, with an emphasis on processing microstructure property relationships in metals and their alloys. So Eric, the floor is yours, and I look forward to your seminar and learning from you.
Okay, thank you, Ankit. It's nice to meet the other person who actually read one of my papers. I appreciate that. So let me see if I can screen share here. Hang with me while I get it all set up properly.
Yep, perfect.
Okay, I get it aligned in there. Okay, I think I'm ready to go. Hide one thing here. Okay. Okay, if you're a student and you have a burning question, don't feel that you have to wait to the end. You could welcome to interrupt me in the talk if you need to. Today, I plan on talking about retrogression forming and reaging of high-strength aluminum alloys, and I'll define what that means, hopefully along the way. Thanks for having me to your Zoom meeting. I'm sure we all wanted another Zoom meeting today. I'll try to make this one fun for you, though. So first thing to do is to acknowledge who funded the work. So the work I'm talking about today was supported by a National Science Foundation grant with General Motors. It's something we call a GOLI project. So that's a grant opportunity for academic liaison with industry. So thanks to NSF and thanks to General Motors, and particularly my colleagues at General Motors, John Carter and Lou Hector, who are instrumental in getting all this work done. Most of the work I'm presenting today really is due to current doctoral student Catherine Rader. So Catherine did most of the work we're talking about today and actually plotted almost all the figures I'm going to show you. And it was work based on initial studies by a former student, Thomas Ivanov, who is now at Sandia National Labs. But Kate didn't do all the experiments herself. We had a number of former students and current students who assisted, notably Matthew Schick, Danny Nicolai, and Dominic Fascitelli. I would also note we had some undergraduates involved too to help do a couple experiments. I haven't listed all of them, but this is all their work. So the first lesson for your students is if you want to be successful, always work with people that are smarter and more competent than yourself. And I've been fortunate to be able to do that. Now, today we will talk about trying to make parts that will eventually go into automobiles. That's the goal. Current automobiles, the structures are usually steel. Now I'm talking about the kind of automobiles that a professor can afford to buy, not something that's particularly exotic. So this is the automobile body in white. Most of this gray area would generally be a steel alloy. The blue areas shown here are what Alcoa was targeting and actually implementing in about 7 years ago as aluminum components for automobiles. What you'll notice is that most of these components are outer body closures and some panels here for the bumpers. So these are places where moderate to low strength aluminum alloys are quite effective. Now, what we'd like to do is to further reduce the mass of vehicles, which increases their efficiency, whether or not it's a gasoline powered or a hybrid or a battery powered. We'd like to start introducing aluminum alloys into components that require higher strength. So let me give you an example of a target component. This would be this region right here. This is called the B pillar. So the A pillar is up here by the windshield. The C pillar is back here. If it's an SUV or a station wagon, it'll have a D pillar in back. This B pillar is one of the most complex and highly stressed components in the automobile body. So if we can get this to be fabricated from a high strength aluminum alloy, it opens up a potential for a lot of mass savings. But even more than that, it opens up the potential to begin forming some other body components nearby that attach to the B pillar out of aluminum. Because of issues with corrosion and joining, it's difficult to have an aluminum component joined directly to a steel component. There are corrosion problems there, as you may know from your courses. So it's not just lightening and getting more efficiency out of the B pillar. It's also enabling additional aluminum to go into other body components that attach to it that will increase the efficiency of future vehicles, we hope. So that's the goal of this project. Now, the hope is to use something like our AA7075T6, which is a very high strength aluminum alloy. Now, 6000 series alloys are currently used. 6111 T82 is a current solution that's used in the automobile production today. A lot of the outer body panels of the Ford F-150, for example, are made from this material with a kind of a patented heat treatment from Ford. So you can see the strength here is reasonable, but there are other higher strength aluminum alloys we would like to be able to use, particularly 7075 in that B pillar. What are they competing against? Well, they're competing against ultra high strength steels. So how do we compare these materials? Well, we look at yield strength here. We look at density. Now, if you have a simple tensile application of the material in a component, you could just divide yield strength by density and get a measure of how effective that material would be in that tensile application. For bending, though, we want to divide yield strength by the square of densities. This is a good material selection criterion for bending. And when we do that, we see that the ultra high strength steels are somewhere around here, where the 7075 T6 material has potential to double the efficiency of use for mass savings of ultra high strength steels. Even a high strength 6000 series, which would be kind of a moderate strength aluminum compared to all the possible aluminums, even that still does quite a good job. So the question is, how do we begin using this material? Well, let's first talk about what the composition of 7075 is. The primary alloying additions are zinc and magnesium, and these together form very effective precipitates. Usually we call them an eta or eta prime precipitate. I'll talk about those a little bit later, but you notice 7075 also has some copper addition. So to get the strength, we have to have the proper temper condition. The T6 being the highest strength temper condition for 7075. So we not only have to make the part, we have to get the part into the proper temper condition to get the strength we want to make that material an advantage. So now we're starting to come up on what the problem is. The problem is that 7075 T6 has a pretty low tensile elongation. It's about 13%. And that's what we're getting in the lab. If you go to the documentation, say for the ASM handbook, this is typically documented closer to about 9%. 6013, not much better. Ultra high strength steels can be quite a bit better. So formability is where the ultra high strength steels have a particular advantage right now. But if we go to elevated temperatures, say 200 degrees Celsius for 7075, we are now suddenly getting formabilities, or at least tensile ductilities, which is one aspect of formability, that are very competitive with the steels. So this is a potential solution to making the components in this material. Some caveats I'll talk about in a moment. 6013, another alternative. Again, you go to a higher temperature. If you go to hot temperatures, I consider these temperatures here to be warm temperatures as far as aluminum forming goes, whereas this is going to be a hot temperature. We can get really great ductilities here. So these warm to hot forming temperatures offer some potential for making parts like the B pillar. Now, the problem is that the heat treatment for 7075 to get that T6 condition usually involves 3 steps, typical steps for any heat treatable aluminum alloy. do a solution heat treatment at 465 to 500. That's right about where the hot forming temperature is. We have to quench it rapidly. 70 to 75, most of the high strength aluminum alloys are somewhat quench sensitive. If we don't quench them rapidly, we won't be able to age them to high strength. So we have to have that rapid quench. And then the aging for 70 to 75 is typically about 120 degrees Celsius for 24 hours. Now, one of the big problems with that is that these temperatures at which we want to form, even the warm temperature, are actually above the aging temperature. So even the warm forming will significantly alter the temper condition of the material. So even if we can form the part by going to warm temperatures, we may not get the strength we want out of it. Okay, so let's talk about the past. Low strength alloys have made a lot of penetration into the automotive market. And these are examples of high temperature formed materials. We can get huge ductilities in the aluminum at high temperatures, and particularly the 5000 series alloys. So here, the Ford GT, the outer body panels were formed by Superform USA, a specialty forming outfit, and they were bought by Ford. And that's a 5083 alloy, not heat treatable, fairly low strength. 150 to 200 MPa is about all we have there. Cadillac SDS trunk for previous edition and the Malibu Max sedan by GM, hot formed to huge ductilities, great for closures, not super great for strength. Now, 5052 was used to form this component by Honda, again, hot forming. Make very complex components, but we just can't get the strength out of these alloys that are able to have this formability. So now, where are we today? Well, we could still use this technology, and it is used. But if we want to introduce high strength alloys, we basically have the following state of affairs that's available for current production and that's in development. The first is to try cold forming. So we can cold form some of these materials if we can get a stable T4 temper. We'll review for you. The T4 temper for aluminum is the temper you have after you solutionize and quench. So all the alloying additions that we eventually want to end up in precipitates for strengthening are locked in solid solution. Now, in that case, we can have a much softer alloy than the T6 and usually get quite a bit better ductility. The problem is that for these high strength aluminum alloys, some don't have a stable T4 temper. So this issue of T4 temper is only good if it's stable. If we take 7075, it doesn't have a stable T4. If we quench it, it'll begin to naturally age. So if we wait more than a couple days, that material is now altered so that we can no longer age it to full T6 strength. So that's a real problem. It's not a process that's available for all alloys. And this is one of the reasons that the higher strength 6000 series are currently used, because many of them do have a stable T4 temper. But the much higher strength 7000 series alloys are not used in automobiles currently, largely because they can't be formed by the cold forming processes that require T4 temper. So an alternative is to hot form. As we saw, the 7075 has very good ductility at hot temperatures. So a current process in development is something called press quenching. So this sheet of aluminum for sheet stamping, which is what I'm focusing on today, will be heated up to a little bit under 500 Celsius. It will then be stamped into cold dies. So the dies actually act to quench the material down while the part is formed. Then it must be immediately aged to get the T6 temper. Now, this is a problematic process for a number of reasons. One is that when you take the material up to that high of a temperature, handling a sheet of it is like handling well-cooked linguine. It wobbles all over the place. You have all kinds of problems with potential distortion. The next problem is you have to have the press quenching the part rapidly enough for some of these quench-sensitive alloys. So that's a real issue. You're pulling a lot of heat into that die set, and that's going to limit how many parts you can process per hour, because the dies will simply heat up and not be effective quenchers anymore. You also have the problem with uneven quenching. So it's a tough process to make work. People are trying to do that right now. An alternative is go to warm forming. That's the 200 Celsius kind of temperature for 7075. And you start off with a T6 temper, and you simply accept any loss of strength that you have while the part's warmed for warm forming. And BMW actually was making a component for the BMW i8 sedan, which is one of these, super $100,000 plus sedans that's hybrid, I believe. They're making, actually, a contractor was making a small door beam for crash protection out of 7075. And I actually talked with the engineer from the Austrian aluminum company that's producing that material, and they were basically not able to figure out how to control that strength loss very much, is my understanding. So essentially what we're trying to do is address that with our new concept for forming technology. Is we believe we can warm form and also get the full T6 strength level afterwards. So that's the crux of what we've been working on the last few years. Now, let's talk about the effective temperature on 7075. So here's some nice work from my former student, Thomas Ivanoff. Here is rupture strain as a function of temperature for AA 7075. Now, all this material down here started in the T6 condition, just to let you know. So here we have room temperature. So we're getting tensile elongations of 10 to 12%. We go up to 200 degrees Celsius, and what you see is that tensile elongation basically doubles right there. And our reduction in area basically doubles too. So here we can get a significant increase in ductility, and we don't have the material being too far above the aging temperature, which was about 120 degrees Celsius here. So we may be able to somehow fix the heat treatment to not lose all of our strength from the T6 condition. If you go to high temperatures, we of course get much better ductility, but then we have all the issues I talked about with hot forming. Once you get to temperatures down here of about 450 or so, you start to get a decrease in ductility because of cavitation and rupture issues, which I won't go into today. But another effect you get is going to the warm temperatures. Here, you get a drop in the flow stress by about a third. Why do we care about that? Well, when we're doing a stamping operation, we have something called spring back. Think about your stress strain curve. Whenever you load something to plastic deformation, you always go through the elastic deformation first. That elastic deformation is held in the material, and as soon as the dies release, that elastic deformation will recover and the part will spring back. Think about bending a coat hanger. You bend the coat hanger and you release it, and even though if it's a permanent bend, some of that's going to spring back towards its original configuration. This is a problem because it means the parts you form are differently shaped from the dies you use to form them with. So you have to compensate the die design for that spring back. By reducing spring back, you suddenly have an advantage for forming these higher strength parts. It makes it easier to make good dies. Okay, so those are all the reasons why we really want to focus on these warm temperatures, but we still have to solve this problem with getting the T6 heat treatment, the T6 strength at the end of the process. So this is basically our plan for the future. The process we're calling retrogression forming and reaging, or RFRA for short. So the goal at the start was to warm form, so form at a warm temperature, while simultaneously providing a retrogression heat treatment. That's a particular kind of heat treatment that even people working in aluminum alloys may not have heard of. So I'll talk about what that is and define it for you. So we're going to combine this heat treatment with a forming operation at a warm temperature. And then we're going to apply afterwards one single reaging heat treatment. So low temperature heat treatment that will recover all of our strength lost during the warm forming step. Okay, So let me step through and describe to you what all this means. Okay, but before I do that, I kind of put a result up front. So by the time I get to the end of this, I'm going to show you how we made this part. This is actually a formed component from an industrial scale forming trials, laboratory industry scale forming trials, to show we actually able to form a part. This is a sheet of AA7075 T6 all clad that was warm formed by retrogression forming, and we were able to subsequently reage it and get the full T6 strength or better out of it at the end. So this is kind of the bait. This is why you need to listen to the science behind it, because we're going to tell you how we're able to do that and control the process. Okay, so I'm going to first define retrogression and reaging for you. That's a historical thing we need to have under our belts before we understand the forming process. We're going to go through the science of how to predict retrogression conditions so we can design a process that's going to work for us. And then we're going to talk about the mechanical behavior that we can get at these warm temperatures during our retrogression heat treatment. And then we're going to put it on trial through the forming trial to produce the results you just saw. Okay, retrogression and reaging. Retrogression and reaging is a particular heat treatment first applied by Senna. He had a patent on this. It was applied particularly to 7075. The goal of this heat treatment is to improve the stress corrosion cracking resistance of 7075. These high strength aluminum alloys are a bit prone to stress corrosion cracking problems. So Senna and Ranesh had a nice paper describing how and why they did this process. The process basically involves taking a material in the T6 condition and heating it up to above the aging temperature for a limited period of time, and then quenching it back down. They called this step retrogression, which was actually not a good application of the term. Retrogression in a dictionary means something else, but they've applied the term and it's stuck. And what that essentially does is it decreases the hardness and strength of the material from the T6 condition. So that's represented here as a function of the room temperature hardness measurement, as a function of the retrogression time of the horizontal axis on a logarithmic scale, all for this temperature of 200 degrees Celsius. So we basically are applying this temperature for this retrogression time. We cool the material down and we measure the hardness. In the T6 condition, we're up here above 90 Rockwell B hardness. After we retrogress for about, here we have, this would be 20 seconds or so, you can see the hardness drops down. So R is the retrogressed curve. And the hardness drops down with increased time at temperature until we get a minimum here. And that minimum right here is a time we call TR star. We can measure where the minimum is, so it's a critical time for us to measure experimentally. But then the hardness goes back up here, and we get a maximum, and we call that retrogression time max. And then the hardness continues to go down. Now, if we take this material that's been retrogressed for a certain amount of time and we apply a reaging heat treatment, we can then recover that strength or hardness that was lost. Let's take a look at that. So here we have the retrogressed material, and then here we have the material after reaging. And what you will see is that this hardness after retrogression and reaging is higher than the T6 hardness was originally. So this is what the retrogression and reaging step process buys you, is actually T6 or higher hardness and strength with improved stress corrosion cracking resistance. Now, this application here for reaging, the reaging times here were about 24 hours at 120 Celsius. So that's a typical reaging heat treatment. It's also the same as the original aging heat treatment to get the T6 condition. All right, so we can go through these two steps. We get the strength here. Now I've drawn a second curve here. This is the retrogressed material, but instead of applying a full reaging heat treatment, what we've done is we've applied a simulated paint bake. What's the paint bake? Once the automobile body is produced, it's painted, and then it goes through an oven to cure the paint. That's called the paint bake. So it would be nice if the paint bake would serve as the reaging heat treatment. And it does somewhat. So you'll see here that we do gain some strength back from applying the paint bake instead of the full reaging, but the full reaging heat treatment is more effective. Okay. The paint bake would be nice to use because it's already in the automobile assembly line and you get to use that for free. So just not quite as effective as the full reagent for 7075. Now, these are kind of schematic curves. I wanted to show you what the real data looks like. So here on the right-hand side is the real data. This is the retrogression curve here. That's retrogression material right there. This is the retrogressed and fully reaged material. And of course, the paint bake is somewhere here in the middle. So our idea is while we're retrogressing the material going along this curve, we're going to use that warm temperature, increased ductility, reduced flow stress to form a part. After the part's formed, we're going to apply that single reaging heat treatment and get the strength back up to here. And that's kind of the process that that BMW is trying, you probably should have used for that component they were making. Now, we have to watch out for something here. You notice that at this TR max value here, once we reduce strength past that time, our recovered strength after reaging is less than T6. So this really is a maximum in the sense that's the maximum time we can allow at temperature for retrogression or for our forming step. So now we're beginning to understand the key scientific aspects necessary to design a process that allows us to make a component. We basically can't go any longer than this. If we want an industrial process, we need to be able to predict what those times and temperatures are that we have to stay within to control the retrogression process as well as the warm forming. So it's an interesting dual body problem. So that's the first place we went with our research is can we understand this retrogression behavior better? Because quite frankly, it was not documented very well in the literature as far as how it changes with time and temperature. But what happens physically? What's the science behind retrogression? Well, here's some work, and basically Park and Ardell, through a series of papers, really sorted out this retrogression reagent quite well in AA 7075. So these are what the precipitates look like in a retrogression reagent 7075 material. There are two primary categories of precipitates that strengthen 7075. One is an eta precipitate. There are actually three different common varieties of that, and one is an eta prime, which is a finer precipitate that's somewhere between eta and what people may consider a GP zone. So in our heat treating steps, we solutionize and quench, then we age. The aging precipitates out eta and eta prime. Now, what the retrogression heat treatment does is at first it dissolves the finest of the eta prime particles. Slightly coarser eta prime particles are transformed to eta. Some new eta precipitates are formed, usually of the eta 1 variety. That's one of the three varieties of eta that were observed. And some existing eta precipitates are coarsened, particularly at grain boundaries. Now, the reaging heat treatment, which is at 120 Celsius for maybe 24 hours for best reaging, that will grow partially dissolves eta prime precipitates and precipitate new eta prime precipitates. So by the end of this process, compared to the T6 condition, which is going to be right there, that's basically my T6 condition right here, I will have some coarse eta at grain boundaries. And then through the rest of the matrix, I'm going to have a mixture of somewhat coarsened eta that's pretty fine, and these new eta prime precipitates formed upon reaging. And that really gives good strength. And the change of the precipitate nature, particularly at grain boundaries, is what Park and Ardell attributed the increase in stress corrosion cracking resistance to. So this retrogression and reaging not only gives us a very good strength as a result, we get better stress corrosion cracking behavior potentially. And now we're going to use this retrogression step right here to also make a part. Okay, but let's predict what times and temperatures we need to do for that. So if we begin looking at hardness, this is room temperature hardness as a function of retrogression time at several temperatures. So we start out here at 192 Celsius, 200 degrees Celsius, a little bit higher temperature. Now, why 192? Because we did all these experiments in salt pots so we could rapidly heat and then rapidly cool the specimens. Great for scientific studies. And our salt will begin to solidify right under 192 Celsius. So it's a practical reason for the lower bound of the temperatures we investigated. So what you will see at the 8 degrees Celsius higher temperature of 200 is that the TR star time has moved to shorter times, and the TR max time has moved to shorter times. So by going to higher temperatures, we're accelerating the retrogression process. This continues at 210 and 220. Now, 220, we get a little bit of contraction here, so something else may be going on. We have the general trend that increasing temperature decreases the time necessary for retrogression to occur, both at TR star and TR max measures. So how do we predict this? Well, one thing is to think that this is a thermally activated process. That makes sense because we're talking about retrogression dissolving or partially dissolving existing precipitates. That's a diffusive process. Can we get a measure of how quick that process is? Well, the natural way to think about this is the activation energy that controls the process. Now, there's a caveat here. This is a complex sort of dissolution. So question is it one activation energy or is it many? Okay, this is a bit of advice for students. As Professor Box, late of University of Chicago, used to say, all models are wrong, some are useful. So let's start off with the simplest useful model we can try. And that's to think about this as a single diffusivity governing dissolution, which will give us a single activation energy. Let's see if that works. Now, to measure activation energy, let me just kind of show you this slide here. Got a little ahead of myself. I just wanted to show here that by reaging, we are fully recovering the hardness for all these conditions. Okay, so now on to the activation energy for retrogression. So reaging still works, as we talked about before. Well, to measure the activation energy for the retrogression, we turn to differential scanning calorimetry. Basically, what you do for differential scanning calorimetry is you take a small piece of material, in this case it was aluminum 7075 in the T6 condition. You put it into a device that will measure the heat input to raise the temperature. Now, you get characteristic curves like this red curve here. As I increase the temperature at this particular heating rate, the heat flow, this is a relative heat flow measure, increases as I approach this temperature right here. And I get a peak heat input required at this temperature that then drops down. Well, what's happening here is that at this temperature, we are dissolving some of our precipitates. So this is an energy going into dissolving the precipitates. If we're heating fast, we tend to overshoot the temperature what the precipitates would like to dissolve. So we actually find the peak at a higher temperature than when we heat at a slower rate. Here at 1/3 the rate, we get the peak here. Of course, the data are a bit noisier here at the slow rate. But we see that this peak temperature shifts from here to here. And that shift is able to be analyzed. We can analyze it to think about an activation energy for that process that causes the peak. And Barksey and Tronta put together this nice equation here. I would argue it's a somewhat empirical equation that relates the activation energy for the process, in this case retrogression, to the peak temperature that we measure. So this would be the peak temperature here and peak temperature here as a function of the heating rate, basically our beta right here, and some constants. B being a constant, peak temperature appears over here too. So if we use this equation, we can then plot this part of the equation versus the inverse peak temperature. And the slope of this should be Q over R. And what we see is using 1, 2, 3, 4, 5 different heating rates, we get a very nice linear plot, which tells us, yeah, activation energy for retrogression is about 95 kilojoules per mole. And this is actually pretty much in line with the diffusivity of zinc and aluminum. So that makes a lot of sense. If zinc is the rate controlling diffusive species, this activation energy is about what we would expect. But moreover, we get a nice, pretty straight line, which tells us that simple model we assumed of a simple thermally activated process is actually kind of okay. So the simple model seems to be sufficient to our needs, even though there may be more complexity going on. It looks like the more complex stuff is a second order effect. Now, what that gives us the power to do is to define something called reduced time. So we can take that activation energy for retrogression and put it into just the 1 over our Arrhenius relationship here. We multiply that times the time for retrogression, and we define something called the reduced time for retrogression right here. So it allows us to compensate time with the temperature we're actually retrogressing at. So by combining time and temperature, we now get a predictive capability. So let me show you how we use that predictive capability. So here we have the retrogression time as a reduced time. So we're using that activation energy to multiply retrogression time by exponential Q over RT. And then we're plotting the hardness here, which is uncompensated. What's happened is all the data at these 4 temperatures are all shifted so that the minimum here at our TR star occurs at the same time, and the maximum here at TR max occurs at the same time if we're using reduced time. So we now know that we have a predictive way to alter temperature and predict how much our time is going to change for this retrogression. Now that's very important because essentially all of our forming operations have to take place to the left of this tau R max value. So if we're going to form the parts, they have to be formed and then cooled down before we hit this value. So now we're able to predict process windows for our retrogression forming process. So we take that, and now let's take that predictive capability and plot a forming process window we can allow for 7075 T6. Okay, here we have it. This is our retrogression time, real time, not reduced time. This is our retrogression temperature. And effectively what we have is we have a target window right here. Now we can go shorter than this if we need to, but this is a hard maximum up here. We cannot go above this maximum without permanently losing strength of our component. So what we think about this is TR star is a target we'd like to hit. TR max is a full stop limit we can't go beyond. So this tells us where we have to study mechanical deformation at warm temperatures. And that's the next step of our study, is now we know what times and temperatures we're allowed to work within. What are the mechanical behaviors at those times and temperatures? Okay, so from here, retrogression, our recommendation is a temperature of about 200 degrees Celsius, because that gives us times from 3 to 12 minutes. Those times are reasonable for a forming operation. And that's what drove 200 degrees Celsius being a good target temperature. Now, after forming, just to remind you, we would try to re-age at this temperature right here. So we try to re-age at 120 for 24 hours to get the full strength back. And that simulated paint bake I talked about before, which we keep trying, is 185 for 25 minutes. That's about what the one type of paint bake process that's used. We do find it doesn't work particularly well for 70-75, but it's better than doing no reaging at all. So again, this is just a practical interest for us. Okay, mechanical behavior, simple stress strain curves. Here's our T6 material. Here is our retrogression and reage material. What we see is we're getting almost identical mechanical behavior. If we retrogress the material, what we find is, boom, we're getting a 10% or so drop in yield strength and in tensile strength. So retrogressing without the reaging, which is what some of that BMW is doing, that seems to just give us a loss of strength. And that's what people have been kind of just tolerating right now. We're getting around that with the reaging step. Paint bake, and not much improvement in this case. We'll show you a separate case where it gives us a surprisingly better result. Okay, that's kind of where we are in the ballpark, and we're getting elongations of 13, 14% usable in the T6. Now, retrogression forming and reaging, we have to do tests at high temperature. So this is just an example of our high temperature setup. Box furnace, we do all our testing in here. And of course, one issue you deal with sheet materials is they don't necessarily behave isotropically. So we would take the rolling direction, and we tested specimens at 3 orientations: 90 degrees, 45 degrees, and 0 degrees to the sheet rolling direction. It ends up that our material is pretty isotropic. We have to do that all the time when we test sheet materials because this is not always going to be the case. Okay, what happens at high temperatures? Here's our room temperature T6 just for reference. Here are the behaviors at 180, 200, 220 degrees Celsius. So what you see is you get that significant drop in strength, but you also get an increased elongation. This is the ductility we're trying to use, and this target temperature looks pretty good. Now, how do we predict the flow behaviors? Well, plastic flow modeling is complicated. Nobody does a very good job of plastic flow modeling at warm temperatures, partly because we don't understand the physical mechanisms by which plastic flow occurs at room temperature very well. So in this case, Mother Nature is actually pretty kind to us. So we take the data from this engineering stress, engineering strain plot. We now plot it as true stress versus true strain. And here's our 200 degrees Celsius data. You can see the drop, but surprisingly, this flow stress right here stays almost constant over, 0.1, 0.15 strain. So we have almost no strain hardening. That's a very interesting result. And that's important to us because it gives us an idea of how we may be able to predict flow behavior at this temperature. Okay, we'll come back to that in a moment. Let's talk about the ductilities we're getting. So at these warm temperatures, we are certainly getting much better ductilities. So our elongation to rupture is plotted here for 3 temperatures, and I'm showing this as a function of logarithm of strain rate. Here is our T6 ductility at 25 degrees Celsius at room temperature. What you see is a significant improvement in tensile elongation to rupture. So we have much better performance for forming at this set of warm temperatures. We also have some strain rate sensitivity. So we now can see that the flow behavior is sensitive to the strain rate. Okay. Reduction in area, another measure of ductility. It's showing a similar behavior. It's very good at elevated temperatures, but we're also getting the same sort of reduction that we saw before as we go to faster and faster strain rates. So we have to be a little bit careful how fast we form. That's the headline of what we take away from this. Okay. Now, how do we predict the flow behavior? Well, because we're not getting any strain hardening that's significant, we can decouple the flow stress from the strain input. We can begin to think about what are classical equations for high temperature deformation. This is the phenomenological equation usually used for high temperature creep. So we ask the question, if all models are wrong, but some are useful, is this model that's very simple, useful for predicting flow at 200 degrees Celsius at warm temperature? Normally, we would think it wouldn't be in general, but in this specific case, because we have almost no strain hardening present, it might be okay. So we took this model, and from this model, we have activation energy. In this case, it's an activation energy for plastic flow. By rearranging this equation, we can measure the activation energy if we have data at constant values of sigma over E. So that's exactly what we plot over here on the left-hand side. logarithm of strain rate versus 1 over T in Kelvin. And we see here, at least for the data sets that are available, we get something close to a straight line. That gives us an activation energy for plastic flow. This is much higher than we got for retrogression. Of course, it's a different process. It's also much higher than we would get for high temperature creep. This tells us that some different physics are going on, something we don't quite understand yet. I tend to think that what's happening is we have an activation energy for the cutting of some of the coarser precipitates that are left after the retrogression process has already proceeded. So again, interesting science to explore, but for practical points of view, we can take that activation energy and we can use the Zener-Holleman parameter here. And as we previously normalized time by an activation energy to give us was basically a reduced time, we can now go here and we can normalize strain rate with this activation energy function of temperature. And plotting the Zener-Holleman parameter here on the horizontal axis on a log scale here, and the vertical axis, the flow stress at, this is about a 0.1 strain, divided by the Young's modulus at temperature, we find that all these data come onto a nice straight line, which my little pen won't let me draw. There we go. So we actually can now, through again, the simple idea of a thermally activated process for flow, predict the flow stress as a function of temperature and strain rate. So now we're getting predictive capability for how much force we need to form the part. All right, so now we can predict the retrogression temperatures and times. We can predict the forces and flow behavior as a function of forming rate. We have the tools to begin trying to form parts at this point. So let's form some parts. Now, again, fortunately, General Motors was able to help us out in this collaborative effort, and they arranged for some forming trials to be conducted at EWI up in Ohio. It used to be known as Edison Welding Institute, but they're more than that now, so they just call themselves EWI. And they had previously built an apparatus specifically for warm forming. So back here is a furnace right there. That's the furnace. That puts a lot of temperature onto our part. We have a part transfer area here that will grab a part through robotics, move the part over here into the die. That's in a large press. This is the front of the large press. This is the top die. This is the bottom die. So the part's moved in, it's stamped while it's still warm, and you actually make a part. Now, how do we figure out how much time at temperature, what temperature to use? Well, we actually used all the tools I just showed you. We were able to profile the temperature for its heating rate, use our thermally activated process ideas to predict how much time we're allowed to heat, how long we should hold at time, how much over temperature we should have, and then allow for the transfer time and cooling the part during transfer. So we're able to predict all of that because of the science we did before. So we got the part into the dies at the right time, at the right temperature. We stamped it. Stamping was fast enough so we didn't cool down too much during the stamping process, and we extracted it, and we were within our forming process temperature time window. And that's what we got. Great, we got a part. Now, we were able to analyze this part for the strains involved, and I have two examples here. This is what the gridding allows us to do. So this region right here has a major strain of 24% and a minor strain of about negative 14%. This is sometimes called the waterfall region right there. So we can kind of see the kind of like water falling down there. And this is pulled in tension along that direction. And it's allowed to contract along the horizontal direction. So we end up with something that's just like a tension test almost. Now, if we go to this region right here, this gives us a major strain of 11% and a minor strain of 3%, which is close to zero. This is a problem because it's very close to something we call plane strain. That is the stress state under which failure occurs most readily for most sheet forming applications. So in this case, this is where cracking would occur. Now, EWI actually tried to form 7075 in this die, and this depth we formed to is about double what they could ever do at room temperature. So yes, it's working great. The next step is, can we get our strength back? So after forming, it's retrogression formed. We need to reage it to get the strength. So we took some sheets that were formed, cut out specimens here and here after we subjected this material to reaging. So we tested as formed or as retrogression formed plus our full reage, and retrogression form plus a paint bake. And we used the standard ASTM E5 specimens for this, like sub-size specimens actually. What do we get out of it? Well, here are results. Now this sheet is actually a 7075 all clad, which means it has a thin layer on top and bottom of low alloy aluminum, which helps to protect from corrosion. And this was the UTS, ultimate tensile strength, of that material in the T6 condition. And then this is the yield strength in that condition before we formed it at all. Retrogression formed, you see we have a drop in the strength here. The paint bake actually got us pretty close in yield strength and back to almost tensile strength, which tells us that the strain we're inputting to the part during forming may affect the reaging process. The full reaging process, you can see we actually ended up with a stronger part than we started with. So this was a fun project for us to work on because we're able to go all the way from the basic idea through the science to support the basic idea to applying that science to design and implement an actual trial process to prove feasibility. And it worked out all the way. Some projects don't work out so well. Fortunately, this one worked out great. So what are the conclusions? Well, we believe we've shown that this retrogression forming and reaging concept works quite well for 7075 T6 sheet. We think it will work for some other alloys. I mentioned the 6013 alloy. We can get some benefit from using it for that alloy, and there are other alloys that may be applicable to, but we've really just thoroughly investigated 7075. We can predict the retrogression forming conditions and reaging conditions to actually make this work well. And we can at least predict the basic mechanical response during the warm forming. There are some details like forming limit diagrams we haven't pursued yet, but we can do a pretty good basic job there. And most importantly, we can do all this, make a part, and get back to a final strength that's better than the T6 condition, at least in this demonstration part. We hope there may also be some benefits to improve stress corrosion cracking resistance, the original reason that Senna invented this process, but we haven't had a chance to look at that yet. Okay, I think that I'm about out of time, so I'll be quiet and listen to you guys tell me what to do next. Thanks for your attention.
Thank you, Eric. That was a great talk. And yeah, now I would like to invite questions. I don't have any questions yet in this chat box. So please go ahead and start typing your questions. But I can actually start to ask if people are still thinking about their question. So Eric, it was really a nice talk and I learned a lot, sort of rejogs my memory when I first did the sheet metal test in the mechanical metallurgy lab.
Great.
Sophomore year. So good on that. So what is the source of, on slide 12, we have shown this inflection curve for the RRA process. So what is that source of inflection that appears in the retrogression and reaging process, the characteristic curve that is shown on slide 12?
Sure. And yeah, you're right. I didn't go into the details here, but during retrogression, we're going to follow the retrogression curve here. Let me go back. There we go. So we have this process going down, and that's the initial dissolution of the fine eta prime precipitates primarily. So we're losing strength as we lose those precipitates, but we're also coarsening some of those eta prime precipitates a little bit and transforming some of them to eta precipitates. And we get some strengthening effect from those, and that strengthening effect from those eta precipitates, the finer eta precipitates, that's what's giving us the strength here. This second peak is that everything is now getting pretty coarse and we have over coarsening. So this is kind of everything is now getting too coarse. Mm-hmm. This is basically initial dissolution. And then this guy right here, a little bit more mysterious, is kind of the eta prime. Some of those go to eta. And we actually get a little bit of strength because this is a more effective precipitate when you have fine eta in this case. That's essentially what Park and Ardell has sorted out. So let me just go a couple slides ahead and just show that's that initial drop.
Okay.
This and this, I forgot to mention that you're forming some new eta too. This is that second step. So this, and this. So these guys, kind of that. These guys are kind of this right here. And then that's that last drop right there. And it's a complicated process. And Park and Ardell does some beautiful work on that. I always am so happy when somebody sits in a dark room and does TEM for hours on end, so I don't have to. And they sorted it all out. They really sorted it out very, very beautifully.
Yeah. So as you say that the coarsen, as the eta actually coarsens, the hardness reduces. So there is an intricate relationship with the grain size.
Well, the grain size doesn't really change very much because we're at too low a temperature for grain growth, and we still have enough precipitates to pin the boundaries. So this coarsening is really just the precipitates themselves. And once we go past the second peak, once the precipitates are coarse, you can't uncoarsen them unless you go back and solutionize everything.
Okay. Yeah.
And that's one of the problems with forming these high strength alloys, because everything you try to do at elevated temperature can dramatically alter the heat treatment. And if you don't do it right, you have to go completely back to solutionization and reaging. And there's no way you can maintain the dimensions of your part by doing that. So it's a very intricate dance to get in between all these very complex processes that are going on. And quite frankly, it's part of the fun is figuring out that dance.
Yeah. Are there any other questions? Krishna, you'd like to go?
Well, some of the students have left. But a couple of them pinged me up and wanted to find out what are the career options for them in metallurgy.
That's a good one.
Yeah, that's a long list, actually. If you want to make anything out of metals intelligently, you need a metallurgist involved. Now, in this case, I'm not developing new materials. I'm simply applying current materials. But you can see the science behind that. So I work with General Motors people that are basically working in metallurgy. Now they're in the R&D, but they also need metallurgists in manufacturing. They have, all kinds of casting, welding issues, as well as sheet forming issues. So there's all kinds of places to go in the manufacturing industry. And look for anybody that makes something out of metals. If you're doing it at a high level or doing any development work, they got to have some metallurgists.
Yeah, so I had a question. It's probably just tangential, but you only did a simulated paint bake, right? You didn't do an actual paint bake.
Right.
You think there could be any minor changes there due to some diffusion of some?
Yeah, there will be actually major changes. The reason we did a simulate paint bake is twofold. One, we can't get access to the commercial production facilities. The paint bake lines cost like $1 billion to make.
Oh, okay.
So, I'm exaggerating. It's huge. So, and the paint bake processes are very, very proprietary by the companies, and they vary from model to model and paint composition to paint composition. So it's always a moving target. Okay. Since we can't deal with that in research, we basically use this, which is what the automobile companies are willing to publicize as a reasonable representation of common paint bake practice. Some of these are like two-step treatments, paint bake treatments. So we chose a simple surrogate for that because there's no single paint bake one can go choose, even if the car companies would tell you about it. So yeah, there will be some changes. And in fact, I think in practice, what the company should do is tailor the aluminum alloy to best respond to the paint bake they will be using. So, that would advise working with aluminum company to do that. It's a good question.
Do I see? I think lots of students have left, at least from the UFA, because they have a class at 12. Students, yeah.
Eric, I actually forgot to introduce Christina. She was also actually on the call, and she is one of the other fellow co-organizers of the MateriAlZ, and she is at the School of Material Science.
Greetings.
Nice to meet you. Thank you very much for the interesting talk. I was a little late because I had a faculty meeting this morning. So, but
I understand.
I hopped on a minute or two after 11, so I caught most of your presentation. Thanks.
Thank you.
So Eric, I was actually looking at your form sample and really very impressive. It actually brings back my memories when I first did the orange peel test in the materials testing lab.
Oh yeah,
so,
that's fun.
So like, are you planning on doing, because yeah, right there, you see, there you go. It's actually much bigger than the orange peel sample I used to have in the lab, but nevertheless, so we all like to drive our shiny cars, and orange peel is really a cosmetic defect, that those surface cracks that may appear because of it's a biaxial tension test, right? So are there like any plans to also, do you guys actually plan on testing, on doing some orange peeling test on these samples?
Yeah, not currently. Basically, this project has kind of run its course for funding. So the next steps would be to do full forming limit diagram construction at temperature, which is challenging. Actually, EWI does have facilities to do that. It's a question of getting the funding to purchase those services. So those are getting towards, I would say, development and implementation aspects. For this process, there should not be any problem with orange peel. We haven't seen any. Okay. We've done a lot of tension tests, and we never see any orange peel effect up to rupture, so huge strains. We don't see any orange peel effect there, and that's twofold. One, we have a fine grain size material that we're not coarsening, and number two, we don't have this kind of roping effect where you have an agglomeration of grains of similar orientation, which is where you also will get some orange peel, or roping as they sometimes call it. So this material just isn't susceptible to those sorts of problems from what we've seen so far. But the forming limit diagrams would be very interesting to see, because it's not clear that it's not clear what the differences between the warm temperature or room temperature will be for this sort of material. And I think of that because I've done forming limit diagrams for high temperature on the 5000 series alloy, and you actually see a dramatic change in the overall shape of the forming limit diagram at high temperatures. Instead of plane strain being the lowest formability condition, balanced biaxial stresses. So things change with temperature, and we were used to seeing room temperature, and people just assume it's going to be the same at high temperature. Bad assumption. Yeah.
That's right.
Yeah. I'm glad somebody else knows about the orange peel test, though. that is a problem at high temperatures sometimes, because you get a lot of coarsening.
Yeah, that's what I like. As far as I can recall, there was some like correlation to grain size, but like you already said, it's already a very fine grain size, and you're not having any changes. So as long as you're able to keep that grain size consistent, should not be maybe a lot of an issue there.
And that's also a problem I expect they will have with the hot forming processes they're trying. I didn't talk about that, but there's a very good chance you could have some significant coarsening effects during the hot forming if you're not very, very careful. So again, I think the hot forming, people are working on that in development efforts. There are a lot of challenges there. So I think if you can get away with 20-25% ductility, I think our retrogression forming reaging is better for that niche.
So as in, I don't know if there are any other questions, but if not, I will just ask one final one. So I would like to know, as a metallurgist, I see a lot of applications going on in the automobiles. How good is Tesla from GM? Or we all want to have a Tesla, right? But then how good is that purely from a metallurgical standpoint?
They are using very, very standard processes and very, very standard processes, usually by contractors that do these processes for other people too. So I haven't seen anything metallurgically interesting yet.
That's knowledge to me, really.
But if you're making a car for over $100,000, you can afford these hot forming processes and things like that.
Yeah, right. Yeah. Interesting, isn't it?
Yeah. Go buy a bolt.
I have a bolt. Hey, Dr. Taleff, it's Arvin here.
Hi, Arvin.
How's it going? So just just to add some substance to your answer before, I was in Professor Taleff's group. He taught me everything I know about metallurgy. And now I work at Intel in Chandler. I'm a technologist here on a day-to-day basis. I work with copper stamping, sintering, alloy making. Yes, there are a lot of opportunities. I just want to make sure that the students get that, and they can always talk to me if they want to learn more about it too. It's nice to see you here, Dr. Taleff.
Wonderful, Arvind, and thank you for letting them know there are opportunities beyond just making cars.
There are many opportunities. Yes.
Arvind, maybe you can help us with, some of the students may be interested in pursuing this.
Yes, for sure. Yeah. I know Dr. Ankit because we were in a hesitation committee. So please let me know if there's anybody who has any questions. I can also help them out.
Sure. Thanks for calling in.
Yeah, I had to call in a little late, but I'm just so glad to see Dr. Taleff after so many years. So always excited to see him. Yeah.
Thanks, Arvind. Work hard. You can be as successful as Arvind someday. You have to be smart too, though. Remember, I said I always hire people that are smarter and more capable than me.
I don't think that's true.
I'm glad you don't, but I do.
So hopefully, Arvind, you're adopting the same. You're hiring people smarter than you.
Yeah, for sure. All the new engineers are definitely smarter than me. I can tell you that. And I'm sure Dr. Taleff has even more smarter students now. But I still think I could be one of his favorites. I don't want to.
I think so.
Oh, thank you, Dr. Taleff. That means a lot.
That's really nice. Anyone else, guys? That was a great talk. That's even if you are not a metallurgist, I'm sure you would have understood a lot of stuff that's going on.
Yeah.
And it's okay. Dr. Eric knows that we are recording it, right? And if it will be,
we are going to share this on a YouTube channel, and then there are other students who may be interested who can simply check your video and learn a little bit about the new process and everything.
So what I can warn you, Eric, is some of our undergrads might watch it and reach out to you for questions because most of them are in class. So they will watch it, and that's what they've been doing, is to reach out, ask about, it could be as philosophical as where do I find jobs, stuff like that, but hope that's okay.
Sure, that's fine. Students are okay.
Yeah.
I like students.
Okay. Hopefully it's not Ankit reaching out to you. Where can I find a job? I don't
like hang together us last metallurgists,
We did have a good discussion on steel microstructure yesterday. So hopefully we can keep that discussion going.
Yeah, I haven't been able to talk about perlite with anybody in years. That was a lot of fun.
Yeah. All right. So yeah, looks like we are already 8 minutes up, but still it was a great talk and I really learned a lot today. So thanks, Eric, for calling in and presenting, giving us the time, and we really appreciate it. And you spread the word amongst your colleagues there. And we are trying to invite more and more experts also spring, and we also plan on doing this next fall. So hopefully more people will sort of get interested as the interest builds on. So I'm hoping for that.
Great, thank you. It was a pleasure. And this is so much nicer than having to fly in an airplane.
I agree. But having said that, hopefully we can all meet in person sooner than later.
Yeah.
Absolutely. Great. Thanks, Eric.
Thank you, Eric.
Bye, Christina.
Bye, Christina. Bye, Krishna. Bye.
Bye, everybody.